This method was built to answer a very real world question. Why do you different groups in the labor market earn different wages? Specifically, it helps us quantify wage gaps by gender, race, ethnicity, and immigrant status. Over the next few minutes, we will cover the background, its methodology, its applications, and I will even show you a live analysis demonstration. So let's get started. Here is our plan for today. We will start with the fundamental question: what exactly is the Oaxaca blinder decomposition? Then we will travel back to the early 1930s, 70s to understand why two economists independently arrived at the same breakthrough. After that, we will get into the methodological framework, the two-fold and three-fold decomposition. We will look at key applications across economics and the software tools we can use to implement them. Oaxaca blinder is a statistical decomposition method. It takes the average outcome gap between two groups, say for example group A and group B, and neatly splits that gap into two components. The first component is the explained part. This is the portion of the gap that comes from observable differences in characteristics. For example, if men have more years of education or more work experience on an average than women, that explains some of the wage gap. The second component is the unexplained part. This comes from differences in the returns to those characteristics, meaning thereby if a woman gets a lower wage increase for the same year of experience as a man, that difference is captured here. In labor economics, we often interpret this unexplained part as a potential signal of discrimination. In 1973, two prominent economists, Ronald Oaxaca at Princeton and Alan Blinder at Yale, published their research papers independently, yet they proposed almost identical framework. Oaxaca's paper, published in the International Economic Review, focused specifically on the gender wage gap in urban labor markets, whereas Blinder's paper, published in the Journal of Human Resources, tackled wage discrimination more broadly. They both realized that simply comparing average wages wasn't enough. You had to control for productivity differences. Their key insight was to ask, if women had the same characteristics as men, what would their wages be? The gap between that hypothetical wage and men's actual wage is what we call the unexplained portion. That's the revolution. These two papers laid the foundation for thousands of empirical studies that followed. Let's formalize the intuition with some basic math. We estimate separate linear regression for each group. For men, our group A, for example, we model wages as a function of observable characteristics like education and experience with their own set of coefficients. And we do the same for women, group B. The outcome variable Y is usually the natural log of hourly wages. This is important because the logarithmic transformation helps us interpret the gap in percentage terms. Now, if we take the mean difference in outcome between the two groups, the total gap, the two-fold decomposition breaks it into two pieces. As I mentioned earlier, the endowment effect is the explained part. It tells us how much of the gap is due to differences in average characteristics. For example, if men have two more years of experience on average and experience increases wage, that 2-year difference contributes to the gap. The structure effect is the unexplained part. This is where things get interesting. It arises because the coefficients for men and women are different. The structure effect can actually be split further into an overpayment to group A and an underpayment to group B, depending on which group's pay structure we choose as the fair benchmark. The threefold decomposition offers an alternative breakdown. Instead of just two parts, it adds an interaction term. Why? Because the two groups might different in both their characteristics and their coefficients simultaneously. And finally, the interaction term captures exactly that. It measures how the difference in endowments combines with the difference in returns. So you get three components: differences in endowments, that is characteristics; differences in coefficients, that is returns; the interaction term between the two. This can be very useful when you suspect that the groups are not just different in skills or in rewards, but that the relationship between skills and rewards itself varies non-linearly across the groups. This slide takes us from the big picture to the granular level. We can estimate the threefold composition not just for the overall gap but by variable. Now let's address a major practical challenge, the index problem. As I hinted earlier, when you calculate the unexplained component, you have to choose a reference wage structure, or do you use the female coefficients? This choice can change your results significantly. To solve this, researchers have proposed alternative weighting scheme. Reimers in 1983 suggested using the average of the two groups' coefficient. Cotton in 1988 proposing a weighted average based on the sample sizes. However, Newmark in 1988 took a different approach, using coefficient from a pooled regression over both groups as the reference. Each of these is a valid attempt to get an unbiased estimate of the true discrimination effect. But the key takeaway here is the results are conditional on your choice, so you should always justify your choice. The flagship application of this method is in labor economics. First and foremost, the gender wage gap. This is the canonical use. By decomposing the gap, we can estimate what portion of the male-female wage differential is due to career choices, education, and experience versus potential discrimination. Second, racial and ethnic gap. For example, comparing white and minority workers. This helps isolate the effects of historical disadvantage and labor market segregation. And third, immigration native gap. Here the decomposition helps separate the effects of language barriers and foreign education recognition from discriminatory treatment. Each application tells a slightly different story about why the gap exists. Researchers have increasingly used this method to understand why health outcomes differ so dramatically across socioeconomic and racial lines. Researchers also use the same method to study the achievement gap, differences in test scores, grades, or graduation rates between students from different racial or socioeconomic backgrounds. Before we jump into the live demo, let's quickly look at the tools available to run this analysis. In Stata, Ben John's Oaxaca command is the gold standard. It handles two-fold, threefold, pooled weighting, and bootstrap standard error. If your outcome is a binary like employment status, use non-linear regression decomposition analysis for logistic models. In R, the Oaxaca and OB_decompose packages offer similar flexibility and they are free. For SAS or SPSS, there are built-in macros, but they are less flexible and harder to customize. For today's demonstration, we will use Stata because it's the most comprehensive and widely used in applied economics. Thank you for the theoretical background.